There, there. All right. Just one more problem to deal with. I think that's good. Get that out of my way. All right. Okay, so freezing point depression is one of those colligative properties. And remember what that means? What's a colligative property? It's one that it's a property that's particular for solutions that does not depend on the identity of the solute. The solvent, yes. The solute, no. So that means we can learn things about the solute, anything that's dissolved in the solvent, regardless of what it is. And freezing point depression is one of them. Boiling point elevation is another. Osmotic pressure is another. And there's a fourth one. It escapes me for the moment. But we're going to look at freezing point depression simply because it's easier to deal with. We could do a lab with boiling point elevation, but that would be even more difficult. So what do we need for this one? Well, we need a solvent, and we need a solute. And the solvent is going to be equal to lauric acid, which is a fatty acid, right? We've all got some of this stuff in our bodies. It's incorporated in true fats, of course, but nevertheless, we use it because its normal melting point is in a reasonable range. It's not below room temperature and it's not too high. And then the solute is going to be benzoic acid. Now, it doesn't matter what the solute is for the property to be effective, for the colligative property to work. But we're interested in the molar mass of this compound. So as a review, what do we need? That's my abbreviation for molar mass. What do we need to know to calculate molar mass? We need to know a mass of the substance, and then how many moles does that represent? Okay, so mass is easy, right? We just weigh out a certain amount of benzoic acid. Then we use the colligative property to determine how many moles we have. Okay, so what's the controlling formula for this colligative property? It's a change in temperature, and the freezing point depression constant that's particular for lauric acid. Okay, and that's given on that first page. You can see right there in the pre-lab question, it's 3.90 for lauric acid. Degree C per mole. Let's see if that far away. Excuse me. Per molal, actually, is the way we write. Per molal. Okay. Remember what a molal is? It's moles of solute per kilogram of solvent. Remember why we have to do it that way? Why don't we use molarity? Because molarity has volume in the calculation. If the temperature changes, the volume changes. So this would never be constant. I mean, this would never be fixed, not constant, but fixed. Every time the temperature changed, the concentration would change. So we need this measurement, molality, reference to kilograms, because mass doesn't change with temperature. Okay, there's more to this formula, right? Times molality. Now we could have a Van Hoff correction factor in here, right? An I. If the solute would dissociate into separate particles, usually ions, in solution, then we'd need a correction factor, but this one doesn't. Benzoic acid is entire. It goes into solution as this whole unit. So our correction factor is actually 1. All right. So that's the theory. What's the practical approach here that we're looking for? Well, we're going to take a certain amount of lauric acid and put it in a big test tube. Things are about that long, about that big around. And you're going to need a funnel. This is a powder funnel. The only difference between a powder funnel and the funnel you've been used to is it's got a big opening, right? Because we're going to put solid through there, right? And if we use one of those really tiny ones, it would get clogged up. So we use a powder funnel. And one of the things we want to do is when we add these solids, they're both solids at room temperature. When we add both of them, either one of them, we want to get as much of this as possible down here. Right? It's inevitable, static electricity and small particles. You're going to get some that are cling to the side. You want as few of those clung to the side as possible, because that's a source of experimental error. So once you get your, I'm going to abbreviate here, La for lauric acid and Va for benzoic acid. Once you get your lauric acid in here, then we're going to submerge it in boiling water. Right? So it's 97 degrees at this altitude, something like that. Okay, so rather than determining the melting point as it melts, we're going to determine the melting point as it refreezes. And those two temperatures are the same. The temperature of melting and the temperature of fusion are the same. So we'll pull it out of this. Right? That's an expanded view here. And we're going to stick a thermometer in it. Right? And it starts off on the way, this thermometer, as the temperature changes, it's going to go from a high to a low. Right? So you're going to have a list here of temperature and time in seconds. You can put the time on this side if you want, that's fine. So we're going to have a temperature here, and I think it says start when it gets to 60 or 70 degrees.
60.
60. So once it gets to 60 degrees, you start your timer. And that's 0 time. Now, one mistake that students often make is they say, okay, we got to measure it every, what, 30 seconds? 30 seconds. So the first measurement's at 30 seconds. The second measurement's at 60 seconds. Believe it or not, students will stop their stopwatch and read and then start it again. But what you've done there is you've added probably 10 or 15 seconds to your time. So you let the thing run, and every 30 seconds, 30, 60, 90, 120, you take a reading. So that's where teamwork comes in. One person's reading the time, and they say time or measure or whatever. And then the other person is stirring this thermometer so you get a uniform temperature distribution and read the temperature. Now with these thermometers, probably the best you can do is estimate a half a degree. Right? They're marked off in degrees centigrade, and between the two, you can maybe get a half a degree. So you may start off at 60 here, and this one, the next one may go down to 58.5 or something like that. But you keep track of that, and you keep reading against time until your temperatures are constant. Okay, once you hit 3 temperatures in a row that are exactly the same, then you can stop. What I've noticed sometimes is the temperature will get down to, well, I don't know. Let's see, what does our problem say? This pre-lab problem says we're in the neighborhood of 39, 43. Let's say it's 43 degrees for the pure substance. And it starts to freeze. You'll see it'll get cloudy. And you'll see in here, not up here on the sides, but inside here, you'll see the formation of the solid. And it'll start to form 43, and then it'll jump up, maybe 44, or even 45, and then it'll go back down to 43. Okay, you can observe this in almost every liquid that freezes. It's called the latent heat of fusion. What's happening is, as the liquid cools, we're extracting heat from it. We're extracting energy. But when it goes from a liquid to a solid, it gives up more heat than you would expect. And the temperature jumps up as it releases that extra energy. See, these liquid molecules are in there moving around, maybe vibrating, and then they get fixed into solid. And when they do that, they're at lower energy. So they got to give up that heat. And sometimes the heat manifests itself as an increase in temperature, and then it'll settle back down. So we don't want this latent heat temperature. We want the temperature when it's actually solid. You can see that with, you can do this experiment yourself with water. You can freeze water and measure the temperature, and it'll be dropping down, and when it turns to ice, it'll go back down like that. Okay, so we do that for the pure solid boric acid. Then we weigh out a certain amount. We have a mass for this one, right? You have to have a mass for that one. So you're gonna have a mass here. And then you're going to weigh out a mass here, right? I don't know what, maybe 8 grams or so, something like that. And then maybe a gram of this. And then you remelt this, right? Put it back over here, remelt it, and then you add your benzoic acid. Okay, and let it dissolve, melts and dissolves. Then you bring it out and do the whole thing over again. And you get 2 different temperature data sets. And then you plot them, right? So you'll plot them as time in seconds and temperature in degrees C. Okay, and it'll go down and you'll see it. It's fairly regular like this. And then it'll level out like that. Now, if this curve is too gentle, sometimes in order to find the exact temperature, you need to extrapolate
or a best fit line like this and a best fit line like that. And then this is the Nelson. Usually though, in this experiment, it's very well behaved and you can use the temperature, that the constant temperature would be best fit. This is valuable, this method where you have these two intersecting lines is valuable when you have a more accurate thermometer, an electronic thermometer. That'll give you 1 or 2 decimal places. Then the difference is noticeable. But with our thermometers where would be doing good to read 1/2 degree, you can go with the lowest, but I still want you to plot it. And then the second time you plot it, it may follow a similar path here, but it'll go down to here before it flattens out. And this difference in temperature is what we're looking for right there. That difference in temperature. And it's an absolute. Right? It doesn't matter if you subtract final temperature minus initial temperature. In this case, it'll work because no, it won't. Final temperature would be lower than initial, so you get a negative number, but we don't want negatives, right? So what we actually want is the absolute value, just the temperature change, right? If you got a negative sign, throw it out. We only want the difference in temperature here, absolute difference. And then we have this value, and we can calculate molality, right? We can calculate the molality of this solute in that solid. And once you have the molality, it says you have so many moles of benzoic acid per kilogram of lauric acid. Okay. So if we're measuring this in grams, right, let's say it was around 8 grams, wasn't it? So you have 8 grams. Actually, you probably get more decimals than that. You can get 4 decimals. Grams of lauric acid. How many kilograms is that? Well, how many grams are in a kilogram? 1,000 grams in a kilogram. So if you have 8 grams, how many kilograms? You have 8.000 times 10 to the minus 3 kilograms, right? Because what? The unit of measure gets bigger, so the number has to get smaller. So that's what goes in here. But from this formula, we get molality. And then we know that molality is equal to moles solute per kilogram solid. We know this one right here because we measured it. And we know this one right here because it came from that formula. So we have an equation in one unknown. Right? We have moles of lauric acid equal to molality times kilograms of, benzoic acid. Lauric acid. There we go. So now we know we can calculate moles of benzoic acid by the molality we determined from that formula times the kilograms that we determined on the balance. And then this moles goes right there. And we already have the mass divided by moles, molar mass. So there you go. It's a very simple lab. Okay, any questions? All right, we've got one pre-lab question to work. So let's do that one. Let's see. This like that. Erase that one. And this one. That. We'll leave that. Okay. Let's see. We're gonna have a value. I'm gonna have to erase this right here. Let's put it over here. That's starting to fade on me. Try this one. Absolute value of the change in temperature is equal to the K, freezing point depression for the solvent times the molality of the solute. Benzoic acid. Okay, and this one is 3.9 degrees C per molal. All right, the values that were given in this pre-lab question: 7.98 grams of lauric acid. 7.98 grams. Okay. And the temperature, its freezing point, is given as 43.75 degrees. Freezing point equals, like read it easier up here, 43.75. So that tells me that they were using an electronic thermometer, one that would read 2 decimal places. So that's the freezing point that was determined from plotting the numbers, plotting values. Then they put 1.03 grams of benzoic acid in it. And the freezing point of the mixture now is 39.43. Okay. That's all the information that's given. These masses, those temperatures, and we need to calculate the molar mass of this compound. All right. So we can substitute values or we can solve for the unknown. We've done it one way, let's do it the other way. So let's solve for the unknown. The molality of benzoic acid in this solution is equal to change in temperature divided by the K value for the freezing point. So now we have, what's the change in temperature? Well, you subtract the two, right? If we subtract this one from that one, then we've already got a positive value, and that eliminates the problem of having to throw away the negative sign. So this would be 2 here, that would be 3 point, and this would be 4 degrees C. That is your delta T. 4.32 degrees C. And then the K value, which was given, 3.90 degrees C per molal. Okay. I always like to check my units to see if it makes sense. This is in the numerator, that's in the denominator. Those two cancel. This is in the denominator, the molality symbol is in the denominator of the denominator, which mathematically means it's in the numerator. So this one comes up in the numerator here. Now we just need to divide 3.90 into 4.32. All right. What you got?
1.108.
Okay, let's see. 3 significant figures. 1.11 actually. I'll tell you what. We're going to do another calculation, so let's keep some extra decimals. 1.108 molal. Okay, so now we need to determine, that's the concentration of the solute in this solution. What we need to do is use that value with this relationship to determine the moles of the solute, which is benzoic acid. So this is 1.108 moles benzoic acid per kilogram lauric acid. So we know how many kilograms, well, after we make the conversion. So if we multiply kilograms times this value, it will cancel kilograms of lauric acid and leave us with moles of benzoic acid. So how many kilograms do we have? 7.98 times 10 to the minus 3 kilograms. Okay. 7.98. And I get 8.839 times 10 to the minus 3 moles of lauric acid. Okay. So now we have mass, benzoic acid. We have that many moles of benzoic acid, which is also 1.03 grams of benzoic acid. So the molar mass is equal to the mass, 1.03 grams divided by the moles, 8.83 times 10 to the minus 3 moles. Okay, I get 1 rounded off, 117. 117 grams per mole. Okay. Now, what's the accepted value? Well, that's right here in the problem. 122 is the accepted value. So the percent error is the calculated value minus the accepted value divided by the accepted value times 100. Okay. And I get minus, let's see, 3 significant figures. Well, actually, it's 5. Actually, it's only 1 significant figure, right? Because the rules say, right, significant figure rules is that minus 5. So we've only got 1 significant figure. So rounded off, it's minus 4%. It's not too bad. Actually, it's really not that good for a researcher who can determine temperature to 2 decimal places and they still get that far away. Okay, so it's maybe what they needed was to measure these out to another decimal place. That would help. Anyway, that's it. That's the pre-lab question. Now, I think in your document, the student version, there's a little bit more. Well, you do have laboratory questions. Those are after the lab. But you have an appendix that explains things in black and white. And then it's a sample problem at the end. So I don't think we need to do that sample problem because the whole thing is right there and they follow the exact same procedure as this. Okay.
In our lab, will we be discarding the solution or stating it? Does it tells you what to do depending on?
Oh, okay. Let me see. What's it say? Right, we're gonna discard. So, okay. So once you get finished with that tube and the mixture, reheat it and pour it into a plastic weigh boat. And then let it solidify. Then it can be disposed as solid waste. What happens if you pour it down the drain? It solidifies in the drain. And the first time may not clog it, but if that happens several times, it'll eventually clog it up. And these are non-hazardous materials, so we can dispose of them as solid waste. Okay. So if there are no questions, then you just need to set up your lab notebook. So Thursday, when we go in the lab, I can check it like I usually do.